Curriculum crosswalk for electrician training now is Thevenin Theorem. Needed obviously for any schooling beyond here, so it's an important theorem. I'm going to erase it.
More important.
It took about 10 steps. This is another thing to consider. It took about 10 steps to find information about this. Okay. Now we're going to talk about Thevenin's theorem. Thevenin's theorem is named after the person who came up with it, of course. And another gentleman who did a similar thing was Norton. So there's Norton's theorem, but we're going to start with Thevenin's theorem. Here's the idea behind Thevenin's theorem. If you had 2 points coming out of a circuit across any element in a circuit, what can I measure between these 2 points? Or consider this, a black box. You can't see the circuitry inside. They have 2 terminals coming out of this black box. What could I measure? Well, one thing I could measure is the voltage from A to B. That would be the open circuit output voltage. By definition, any voltage that you measure between 2 points that you define, once you define the 2 points, the open circuit output voltage, we'll be calling V Thevenin. VTH stands for V Thevenin. What's another thing you can measure? Couldn't I get it? So in other words, I could put a voltmeter and measure the voltage coming out of this circuitry of this black box. I could get a ohm meter, and couldn't I put an ohm meter on here and measure the resistance from A to B? And that's the resistance looking back into terminals A and B. Another thing that you can do, but this is for Norton's only, I can find the current from A to B in a short circuit. But you're not doing that for Thevenin's, that's why I have it in parentheses. But another measurement you could take, couldn't I put a wire here? I could find A to B in a short circuit between points A and B. So if I put a wire here, I could measure the short circuit current. So sometimes that's called like the black box theorem, black box theory, where no matter what circuitry is in here, if I bring 2 points out, I can at least measure the voltage out, the resistance looking back in, and I can short it and measure current. And I can do that mathematically, or in the real world, I can actually do it in a lab, but you can't normally short something out in lab, right? It's not a good thing. You have to know enough about the circuitry where you know you don't shorting is not destructive. You can't measure the resistance looking back in an active circuit, but we learned if you cut on that if you put a rheostat on and adjust the rheostat so you get half the voltage, the only way you can get half the voltage is if the voltage across the rheostat, a variable resistor, matches the internal resistance is the only way you could get half the voltage. In other words, you measure the voltage before putting a variable resistor on, then you adjust it for half the voltage. The only way that would happen is if the voltage here was the same as the voltage across all the internal components in that box. Well, if you can do that, what can be in this box is this: an equivalent circuit that consists of the Thevenin voltage and a series resistor that you call R Thevenin, and it comes out to terminals A and B. That is the Thevenin equivalent circuit. And the idea of this is to take a complex circuit convert it to this simple circuit. In essence, what's happening is you're going to take what's in this dotted line, in my example coming up. This is the box. And this resistor that I labeled RL is the resistor that I'm going to open or take out of the circuit to find the Thevenin equivalent. But to see more about what this really means, what I got to do is solve this for Thevenin's first, because it doesn't mean much until I show how to solve for Thevenin's. So to do Thevenin's, the first thing, it doesn't matter order. You can find V Thevenin, you can find R Thevenin. What I'm going to do is find V Thevenin. Which is equal to the voltage between A and B with RL removed. Okay, now I got to talk a little bit about what we mean by RL. This RL, should move it on the other side because it's really what's outside the box. RL. This RL is our resistor of interest. It's like this could be an amplifier, and that's the 8-ohm speaker on the output. This could be a instrumentation amplifier or a motor amplifier that drives a servo or a stepping motor or anything. Something that drives something else. That's a very common thing in the world of electronics. It's sometimes difficult to explain at this point, but you kind of have the idea that circuitry might control a DC motor, and the DC motor does something based on the circuitry. Well, this is like the motor that's being driven by the circuitry. And I'm just showing a bunch of resistors because that's all we know at this point. So RL is the resistor of interest. To do Thevenin's, according to what we said here, the Thevenin's voltage is the open circuit output voltage. Open circuit means that if you have a load on there, you remove the load. So you remove this RL. As soon as I remove the RL, the circuit is going to look like this. And you label the terminals where you remove the load, A and B, arbitrarily. So this 2.7K that I labeled RL, I remove it and I label the terminals where I removed it, terminals A and B. So on my schematic here, it's like just erasing that for a moment. And we're going to put it back in later. These Thevenin's is designed, or is defined as the voltage from A to B with the load removed. Another way of saying that is it's the open circuit output voltage. I set it over here, open circuit output voltage. And that's V Thevenin. Now notice resistor 3 is aiming down. I just turned it up. Is it legal to put that resistor up? Would it make any difference if I brought a wire out here and had it pointing down? Absolutely no difference. This is just a more efficient way of writing it, that's all. Now this is important. How much current is flowing through resistor 3 in this example now? 0. Yeah, it's an open circuit. No currents flowing through resistor 3. If no currents flowing through resistor 3, what's the voltage drop across resistor 3? 0. 0 voltage drop. 0 potential difference. Another way of saying that is no difference in potential between one side and the other. If there's no difference, how do we say that? It's the same. No difference means the same. Therefore, the voltage at this point is identical to the voltage at that point in an open circuit. That's a very important principle in all of electronics, all the things that you do. When you have a component hanging out in space, there is no voltage drop across it, yet it's an electrical connection from there to there. So can you electrocute yourself when the wire is hanging out in the open? Yeah, because as soon as you touch that, if you were touching this, wouldn't you now become a load onto the circuit? So you have to assume that the voltage there is identical to the voltage there. So again, an open circuit like this, if zero current's flowing, V is equal to I times R. Zero current times any value of resistance is 0 volts. 0 volts means zero potential difference. No difference means the same. The same from here to here. Therefore, isn't the voltage from A to B the same as the voltage drop across resistor 2? Because any current that leaves the source, it only flows through R2 and R1, establishing a voltage drop across R2. And what do we have going out to terminals A and B? V2, correct? So, V2 can be found by the voltage divider experiment. Aren't those two resistors in series? So using a voltage divider, I can find V2 by taking the total voltage, V total, times that resistor, R2, over the sum of R1 plus R2. That's the voltage divider equation. Or could I solve it like a series circuit? Say 2.2K plus 3.3K is 5.5K. 50 volts divided by 5.5K, find the current. The current times resistance gives you the voltage there. And I also have the voltage at A to B. So this is 50 volts, 5, times 2.2K over 2.2K plus 3.3K, which is 5.5K. So divide 2.2, the way you do this in your calculator is 2.2K divided by 5.5K equals, then times 50, and you should get 20 volts, right? Yes.
Is this going to be on the final?
Yes. Even if it wasn't, do you think I'd say no?
No.
You'd go to sleep. I can't let you sleep. So, what did we say the open circuit output voltage was? The Thevenin. So we did find the Thevenin equivalent voltage. Whatever that means at this point. I know you don't know what that means yet, but you will. We already got one part. Part 2. Find R Thevenin, which is the resistance looking back into terminals A and B. It's RAB, which is the resistance looking back into A and B. And that is R Thevenin. So we have to draw the circuit. We replace the power supply with its internal resistance. Remember in superposition, the internal resistance of a power source is 0 ohms. With the short circuit, we have the identical circuit as above. And it's the resistance, R Thevenin, is the resistance from A to B, looking back in. It's like finding R total, but from the opposite side of the circuit. So let me ask this. What is R total from the point of view of the supply? The normal way you found R total, what is R total in this circuit? What's our total?
6.68.
How much?
4.68.
5.5K. It's just adding these two resistors. Wouldn't current leave here and flow through R2 and R1? So it's 3.3K plus 2.2K is 5.5K, isn't it? This resistor is not even in the circuit because there's no path. So from the point of view of this source, What does our total mean? It means, what is the source C as a load on it? The source C's just R1 and R2 across it. That's our total in this circuit. But our Thevenin is never our total from the point of view of the source. Our Thevenin is never our total from the source, because our Thevenin is putting an ohm meter out here. And how does an ohm meter work? Doesn't an ohm meter supply a little bit of current to see what resistance exists out there? Or another way of looking at it is, if I put a source out here, if I put a source of voltage here, okay, could you guys not talk? It gets, whoever's talking, please stop. If you put a source of voltage, here, would the source of voltage cause current to flow? So current would leave here, split two ways, then go through resistor 3. So from the point of view of a source here, doesn't current leave, split amongst R1 and R2, then all flow back through R3? So that would be R1 and R2 in parallel, getting an equivalent resistor, then you'd add R3, right? Yeah. Okay. Current left, it splits amongst these two, so these two resistors are in parallel, then it all flows back through resistor 3. That's a different total. It's a total from the point of view of looking back into the circuit, not the point of view from this source. Okay? So our Thevenin is the resistance looking back into A and B terminals. So what I would show here is that our Thevenin is the resistance from A to B. I'll actually write it first. So the resistance from A to B is R1 in parallel with R2, I'll just put parentheses around it, plus R3. If I did it in one step, would it be R2 in parallel with R3, excuse me, R1 in parallel with R2, plus R3. So that would be equal to 3.3K in parallel with 2.2K plus the 1K. So what's 3.3 in parallel with 2.2? Around 1.6, something like that. What is it? 1.32? 1.32K? Oh, that's a lot. Plus 1K is 2.32K. That's the resistance. If you put an ohm meter here, isn't that the total resistance looking back in? Now you're more advanced now. Is it okay that I did this in one step? But couldn't I say step 1 is get R1 in parallel with R2, get RA, then redraw the circuit, it's R3 plus RA, same difference. So that's the resistance looking back into terminals A and B, and that is by definition our Thevenin. Step 3. Draw the Thevenin equivalent circuit. And place the load back on. So what is the Thevenin equivalent circuit? It is always a power source and series resistor. It is always this. This is our Thevenin. This is V Thevenin. Our Thevenin is 2.32K. V Thevenin is 20 volts. And this is terminal A and terminal B. And notice that A was more positive than B, so I show this source in the proper direction. Then what do? You take the load that we originally took out, this 2.7K, and you put it back on here.
What does that say? Draw the equivalent what?
The Thevenin equivalent circuit, CKT. Those are common industry abbreviations. I gotta get used to telling you that that's true. CKT is a common abbreviation for circuit in the world of electronics. This is just abbreviating Thevenin equivalent circuit. And our RL was 2.7K. Now with this little circuit, Can I now find the voltage drop across RL? Sure. So that's fine. The voltage drop across RL is equal to the total voltage, because we can use voltage divider equations, can't we? Total voltage times RL over R Thevenin plus RL. Now, can you do it by normal series circuit techniques as well? Of course. But this R over the sum of the R's is the ratio times this voltage source. That's the voltage divider equation. The resistor we're looking at over the sum of the resistors times the total. So that's 20 volts times 2.7K is RL over 2.7K plus 2.32K is 5.02K, is that right? No, 5, what is it?
Yeah, that's good. So
5.02K. So on your calculator, you go 2.7K divided by 5.02K equals, and then times 20, and what do you get?
10.76.
I bet you get 10.76 volts. And then to find the current through the load is simply the voltage divided by the resistance. I is equal to V over R. I'll just show this as sit on it like I usually do. So the answers you got here are 10.76 volts and 3.984 milliamps. You got the same answer as when we did it by Ohm's law over there, right? I'll let you get done writing and I'll explain this, the significance of this. Remember, Thevenin's theorem and Norton's theorem are advanced theorems with the engineering aspect of electronics.
So you said for us, we needed to do that first, but you really don't.
Oh, no.
With Thevenin.
Right. No, that I need to do that first. You don't need to do it first. I need to do it first to prove that when we got answers over there, these answers match. Otherwise, you wouldn't believe anything I said. No, you do not have to do this. This is for me to demonstrate that it came out the same. Okay. What we did now is we got a Thevenin equivalent. We came up with this thing called the Thevenin equivalent circuit, and we found the voltage drop across this RL, the current flow through this RL, and it matches the voltage that we got across and the current through RL when it was in this bigger circuit. There's a point A and a point B here where 2.7K is. I put a dotted line around all this circuitry here. That's equivalent to the box around this, which really means this. If I put a dotted line like this, when I put a 2.7K between A and B here, isn't it identical to putting a 2.7K between A and B here? Can't you interpolate from that that this dotted line represents a bunch of circuitry here? This circuitry is equivalent from the point of view of that load resistor. This circuitry drives that load resistor just like that circuitry drives that load resistor. That circuit is equivalent to this. Or another way of really looking at it, this circuit is equivalent to the original circuit in terms of that load. Now, why is it important to see this equivalent circuit? What if I had a job in the world of electronics, and in this job I have an amplifier that's what's called an instrumentation amplifier. It's taking information from transducers on the job from some system, and this instrumentation amplifier drives a load, and the load is what the instrumentation amplifier would drive. It drives some system that does something. But the system that does something could be a number of different possible loads. And I want to know the effect of driving any resistor from 1K to 100K here. Any resistor from 1K to 100K. So 100 possible resistors here. How many steps did it take to find the voltage drop across and current through here? About 10. Remember we just did the problem? I did a few extra steps in there that I wouldn't need to just get that one component. But say even it took 8 steps. And this is a small circuit. If I expanded this, it might have taken, to get the voltage drop across and current through that, if I added just a couple more resistors, it might have taken 30 steps to get to the voltage drop across and current through that resistor. Now I got to do it for 1,000 resistors. Well, obviously you'd have a computer do that, you know, if you really had to do that. But I have to go, I want to know the range from 1K to 100K. I want to know how that circuit would drive that resistor. And what if it was 30 steps to get to that? Well, 100 times 30, you're up at 3,000 steps to do that. But alternatively, what if I found the Thevenin equivalent? Then I put in a different load resistor 100 times here. How many steps do I have to do to compute it? Only 2. Isn't that better than 30? Now maybe I had to do, in order to do this process, depending on how complex the circuit is, this might take many more steps. This happens to be an easy circuit. It only took small steps here. But what if finding the Thevenin equivalent took 30 steps, but you only do it once? Once you have the equivalent circuit, it's tiny. Now in this tiny circuit, when I change this resistor, it only takes 2 steps to get to a solution. So even if you're programming a computer, what is better? What if it's a complex system and you're programming a computer? If you program the computer to use an equivalent circuit, the computer would be 30 times, 100 times, 1,000 times faster, depending on how many changes you make to the circuit. So one reason for doing Thevenin's equivalent is to take a complex circuit and reduce it to this equivalent circuit of a voltage source and series resistor. Then as you change that load, it's simply 2 calculations to find the voltage and the current. That's one reason. Now, which resistor did I call load here? I just picked one that I called the load. We're going to do this later, but just let me make a point. Don't draw this or anything right now, because I'm going to do this later. This was the this was the Wheatstone bridge. The Wheatstone bridge has this form. Is any resistor in series with or in parallel with any other resistor? No. Can you use normal series parallel techniques then to solve that circuit? No, it's impossible. That is an impossible circuit to do, where you have to combine 2 elements at a time. So what other theorem did you learn that you could solve this? There's one that you've learned already that would do this. Mesh, yeah. You make a loop here, you make a loop here, you make a loop here. You have 3 equations with 3 unknowns. It becomes a mathematical exercise, doesn't it? But with Thevenin's, since typically what you're concerned with is the center resistor, what do? You remove it. You call that the load. And what's the first thing you do? You remove the load. Because what is the definition of Thevenin? It's the open circuit output voltage between terminals A and B. If you remove that resistor, now, what kind of circuit do you have?
2 series.
Exactly, 2 series. These 2 resistors are in series, those 2 resistors are in series.
Add them all up.
It is now solvable, isn't it? Because you have 2 series branches in parallel with each other. You can solve this circuit. So that when you had the resistor here, you could not solve it by normal series parallel techniques. You had to use some network theorem. So that's another reason. Then, look at this circuit that you've already done. The T with 2 power supplies. Which resistor do you think you'd want to remove to make this an easier circuit? Yeah. Look what it looks like when you take that out. Looks like a simple series circuit, doesn't it? Isn't that a hell of a lot easier to solve than when you had that resistor in the middle? If you can make a Thevenin equivalent, we'll do this later. If you make a Thevenin equivalent, then you put the resistor that was here onto the Thevenin equivalent, find the voltage drop across and current through, then you put it back in where you know the voltage across it, you know the current flow through it. Then using Kirchhoff's law, knowing the sum of the voltages in this loop adds up to 0, you know this voltage, you know this voltage, it's easy to find that one. You know this voltage, you know this voltage, it's easy to find that one. It's a lot faster than using mesh or superposition. And an offshoot of this theorem is called Norton's theorem. Norton's theorem makes this circuit a snap. You short circuit here, and look at this. When we do Norton's, would any current flow over here from this power supply? No, it's shorted right there. All this falls away. You do 1 Ohm's law calculation. V over R, you got an I. From the point of view of this supply, does it see anything over there? No, it's shorted. So what current flows here? V divided by R to get I here. So V over R to get I here, V over R to get I here. You got 2 I's. 1 I that this makes, 1 I that this makes. What do you think you do with those? Atom, exactly. Algebraically, you now know the short circuit current. That's going to be what's called the Norton generator. And the resistance looking back into here will be just these two in parallel. If you replace that by a short, that by a short, this is A and B. You'll literally see this resistor down is like down here, this resistor is down here, they're in parallel. You have R Norton, and you solve it like that, 2 calculations. So it's incredibly fast to solve this circuit with a thing called Norton's, which is very similar to Thevenin's. The reason I'm bringing this all up now is you may be wondering, why am I going through all this? But believe me, you save huge amounts of time knowing these theorems. You'll find later with Norton, you can have a transistor amplifier, the output of a transistor amplifier, if you make it the Norton equivalent, it makes it incredibly simple because the transistor by its very nature is a constant current source. And if you understand Norton, you save a huge amount of calculating and you have a better understanding, which is the main thing. So it's the reason behind the madness. Okay. So let me hit this one more time, the process. First of all, you have a circuit. The resistor that bugs you, or the resistor that is of interest in you, is the one that you call the load. What if I was interested in what's going on with that resistor? I would call it the load. I'm just using it as a term to differentiate it from other resistors. So any resistor in the circuit can be the one that you call the load. In terms of the real world, many times a load means it's the output device that's controlled by the input circuitry. That is typically what you mean by that. Like the city of LA is a load on the power grid. The city of LA is like the load resistor, and the power grid is all the stuff that drives wherever you're looking in the power grid from LA. So that's one thing. It's the one you're interested in. Or it's the resistor that bugs you. Now, what do we mean by the resistor that bugs you? It's that center resistor in the Wheatstone bridge I just showed you. In the T circuit, it makes it simple to solve when you remove that center resistor. So the act of removing a resistor is one going to help you, then that's the one, that's the points that you're going to Thevenize. You're going to label the terminals A and B. Wherever you remove a resistor, where that is the resistor that will help you solve the problem. Yes?
The only thing I'm struggling with is why step 1, R3 is not.
Okay, let's go through the whole thing again, and we'll get to this. Okay, so in order to teach this, what did I do? I just picked some random circuit, doesn't matter what. I picked a resistor as, quote, the load, and what's the first thing I do? I remove that resistor. When I remove the resistor, it looks like this. There's no load. Now R3 pointed down, but I just bring it up. Why did I bring it up? Because it just looks funny. You know, if I did this and put A there, isn't that the same thing? So I just put it up here. This was R3, and R3 was 1K. So you remove the load. The first step in Thevenin's is if the load is not already removed, you remove it. Now, sometimes you're Thevenizing where it's something driving something, the terminal is just hanging out there, and you haven't even put a load on it yet, and you're making the Thevenin equivalent. So, in other words, the load could already be gone. You know, a circuit where you're looking at 2 points means the same thing. In this case, I removed RL. I want to find the open circuit output voltage. The open circuit output voltage, open circuit means no load, no path. So I removed the load. You label the 2 points where you remove the load A and B, just for reference purposes. Now in this case, when I remove the load, resistor 3 is hanging out in free space. If I redrew it like this, effectively this is the circuit. But I have a resistor hanging out here too. So it's like a voltage divider. These two resistors, if I straighten the one on top, isn't like a voltage divider, you're dividing voltage up. This is V2, and this is V1. If that was labeled resistor 1, that's labeled resistor 2. I find the voltage there and the voltage there. How much of this V2 gets out to this point? Well, the voltage that develops across this resistor is equal to I times R. How much I is flowing through that resistor? 0, because there's no path. Since no current is flowing through there, 0 times any R is 0 volts, correct? What's the definition of voltage? Potential difference between 2 points. 0 volts means no difference between these 2 points. Meaning whatever you measure here is identical to measuring there. That's very important in the world of electronics. When you have an open someplace, you tend to measure all the voltage. If you're working on a car and you measure 12 volts, people will sometimes interpret that as, well, power is applied. But couldn't that mean that you have power coming to this point, but the load is gone? It doesn't tell you anything about that load, does it? The load could be gone and it's just hanging out in free space. You got a wire hanging out there. So whatever you measure here has got to be the same as there, because there's no difference. No voltage here, yet there's still a connection. No voltage across, but this point's identical to that point. So no difference is the same. This point is the same as that point. Therefore, if that's true, the equivalent circuit is this. Isn't this equivalent to having A here and B here? That's the equivalent circuit of this. A is really that point if no current is flowing through that resistor, and B is really that point in terms of measuring voltage. Okay, so the open circuit output voltage, therefore, is simply the voltage drop across resistor 2. You can neglect this entirely. Isn't that a simple series circuit? Do you know how to find the voltage across the resistor in series? Of course. Now, I chose to use the voltage divider equation. The voltage from A to B is the same as the voltage across resistor 2, again, because this has got no voltage across it, so it's the same. So it's the total voltage times the ratio of this resistor over the sum of the resistors is how the voltage divider equation works. Remember, the current divider was the opposite resistor on the top? The voltage divider is the same resistor on the top. So it's R2 or R1 plus R2 times the total. We came out with 20 volts. That's our Thevenin. That means, by the way, that whenever you find Thevenin, it doesn't have to be smaller than the original voltage in your circuit, because you're dividing it down someplace with some components there. So Thevenin is always going to be less than your starting voltage. So we got 20 volts. That 20 volts is what you label this voltage source in this equivalent circuit that always looks the same. It's always a voltage source and series resistor. The voltage source is labeled Thevenin. The series resistor is labeled Thevenin. That voltage is always, or that circuit is always the same. It's a voltage source and series resistor. So this 20 volts that we found, we label this 20 volts. Then we have to have the series resistance. What does that series resistance mean? It says, what are all these components looking like if I put an ohm meter from there to there? If you put an ohm meter from here to here, you would measure the equivalent resistance looking back into these terminals. Yes?
Does this formula ever change?
No. Voltage divider formula, in terms of the ratios, no, never changes. It's always the resistor you're looking at or the sum of the resistors.
In all three steps?
Pardon me?
In all 3 steps?
No, there's no voltage. There's voltage divider down here.
I'm saying, but the way that it's written out right now, that's the way it stays.
You mean steps going this way?
Yeah.
Well, it's the total voltage times the ratio of the resistor you're looking at over the sum of the resistors. Yes, that never changes. If it's 3 resistors in series, it'd be 3 resistors added up. Now, if you don't like, if the voltage divider equation bugs you, you can always go back to the fundamentals of series. You know other ways of doing it. It just, this saves time to me. That's all it is, time saver. Yeah.
So, we can see the insides of the circuit, but didn't you say it was like a unknown black box? Is that for the sake of demonstration?
For the sake of demonstration, but it actually, you could, in an unknown box, assume a Thevenin equivalent. You measure these and it would be the Thevenin equivalent. You still wouldn't know what the circuitry inside, but you know if you put a load on what's going to happen to it. Yeah. Okay, so how do you find R Thevenin? It's the resistance looking back in. Now R3 comes into play, and the power source is replaced by its internal resistance. It's as if you put a battery here. What would this battery see as R total? Now let me just ask us, what's R total in this circuit again? 5.5. It's simply R2 in series with R1, right? This isn't even in. So this power source sees 5.5K. Is that R total R Thevenin? No, it never is. R total is never R Thevenin. So if I put a battery out here, on the output, and I found R total as if this was the circuit, that would be R Thevenin. In other words, what does this battery see as a load? Doesn't current leave, split amongst these two, so these two are in parallel. Then all flows through R3, which is in series. Once you find these two resistors in parallel, find the parallel equivalent, then add it to 1K to get R total for the point of view of that supply. So when I say resistance looking back into a circuit, it's as if you put a power supply at the output terminals, and what would this power supply see as R total?
Parallel
it sees
R1.
R1 and R2 in parallel plus R3. R1 and R2 in parallel plus R3, so it's 2.32K. So when you say resistance looking back in, it means a different perspective. R total up here is looking that away. R total here looking this away is R Thevenin. So looking back in. So you got R 2.32K. Where does it go? Down here. That value becomes this R Thevenin. So what did you find? V Thevenin is step 1. R Thevenin is step 2. Now what do you do with it? You draw the Thevenin equivalent circuit and throw the load back on and find the voltage drop across the load and the current through the load. That's a simple series circuit. You use series circuit techniques. I chose to use a voltage divider here. They could use normal series techniques. And when we got these answers, didn't they match the answers in our original circuit? And that's why I did the original circuit. Would it mean nothing if I just did that and got answers? But you saw, using normal series parallel, that we got the voltage here, and we found the current here through this load resistor, and it did, in fact, match our result using Thevenins. Then again, why do we do Thevenins? Because what if we had to change many RLs? Let's assume it's a bigger circuit, it took 30 steps to solve. How many steps would it take to get the Thevenin? Probably the same, close to 30 if you had to do a big Thevenins. But then after that, every time you change this resistor, how many steps is it? Only 2. That's a big deal. If you're trying to analyze a circuit and you reduce it to an equivalent, every time you change a load on it, it's this simple circuit that all you have to do is think about this. You don't have to think about all that trash. So that's one reason. And the other reason, what was it? When we have a circuit where the resistor makes it complex, the very act of removing a resistor may make the circuit solvable. And that bridge is an example of that. Before we removed that center resistor, you did not have a methodology to solve it other than 3 simultaneous equations and mesh, which is a complex analysis. But once you remove that resistor, it's a simple circuit to evaluate. Now that your brains are half full, you can take a break and I'll fill it the rest of the way when you get back. Now when you come back, what I'm going to do is